Most physics courses begin by studying mechanics. Mechanics is the study of motion, and this is probably a good place to start for a couple of reasons. First, we all have a natural intuition and curiosity about motion. Most of us are probably watching this bug crawl around the screen, and our eyes are drawn to it, and we're curious about it. Why is the bug turning when it is? How long is it going to be out of frame? Where is it going to come back? What's making him do these little jigs and jogs in his path? We're naturally curious about motion. So this is a good place to start our study of the world around us. The place to start in mechanics is with what's called kinematics. Kinematics is the study of how things move without worrying about why they're moving the way they are. Kinematics is where we learn to describe motion, to write down some terms and write down some equations that describe for us the way something's moving, but we're not yet going to worry about why things are moving the way they are. That'll come later when we look at Newton's laws and energy and momentum. For now, we're just going to describe motion. What we're going to do first is to lay down a set of terms and definitions so that when we use certain words in the context of physics, we all mean exactly the same thing by them. What I'm going to do for you today is to compile sort of a kinematics dictionary. We are going to get a set of kinematics definitions. And the importance of these is so that we all speak the same language. When one of us says, for instance, average velocity, the rest of us knows exactly what that means. And if we needed to calculate it, we could. When one of us says instantaneous speed, we would know what that is, and we would all mean the same thing by it. So this gives us the chance at the beginning to define a set of words that we're all going to understand the exact same thing by. So we have some common ground to talk about and describe motion with. So what I'm going to do here is I'm going to write down the names of all of these terms, and then we're going to go one by one, define them, talk about them, and get some understanding of what they mean. After we do that, we'll look at some examples and put them into practice. So let me list for you the terms that we need to define here. The first one is position. If you're interested in the motion of something, the first thing you have to know is where it's located. And that's what the position vector tells us. In fact, if you were to summarize the term mechanics in as few words as possible, you would probably say something like, mechanics is the study of the position vector and how it changes in time. That's really what mechanics is about. So the first thing we're going to define here is the position. After that, we'll define a term called displacement. We'll see that displacement means change in position. Then come two kinds of velocities. We'll define average velocity, and we'll define instantaneous velocity. Now, after we define these velocities, we'll define two kinds of speed. In physics, we make an important distinction between velocity and speed. So we'll define average speed, instantaneous speed, and last come two kinds of accelerations. You can probably see the pattern, and you see what's going to happen here. We're going to define average acceleration and instantaneous acceleration. Okay, so these are all the terms that we need to define. And I'm going to start doing that by removing this video of the bug crawling around, and we're going to replace it with a plot of one possible path that the bug might have taken. So let me erase this, and I'm going to replace that with a plot in the XY plane of what the bug's path might have been. And let's suppose that maybe the bug crawled along this path, so that at one time the bug was located right here, and he crawled along, and sometime later, bug was located over here. The first thing we want to define is the position of the bug. I'll draw that in red. The position is a vector that goes from the origin to the bug's location. And it looks like this at the other location over here. We can give names to these two locations. If we call this one the initial location and this one the final location, then these position vectors are called r sub I, the initial position, and r sub f, the final position. And we can define now the position vector as r, and it locates the bug as time goes by. So we can imagine as the bug crawls that this position vector follows the bug and it sweeps over here to the right and then down, and it's getting longer as the bug gets farther away, but this red vector just traces out this path as the bug crawls along. We can express this vector in terms of its components. The vector has a component along the x-axis that I'll draw here. We'll call it x. And the vector has a component along the y-axis that I'll draw here. We'll call it y. So the bug's position vector is x I hat plus y j hat. I hat is the unit vector along the x-axis. J hat is the unit vector along the y-axis. Now the next thing to define is the displacement vector. And I'll draw that also in red. And it tells you how the position vector changes. If you go from the initial point to the final point and draw that vector so that it looks like this, that is the displacement vector, delta r. So the displacement is delta r, and what it literally means is change. That's what we mean by delta, change in position. And you can see where that word change comes from if you look at the vector relation among the three red arrows that I've drawn. The initial position plus the change in position equals the final position. The vector equation that relates those three is the initial position plus the change in position equals that lower red arrow, the final position. We can rearrange this and solve for delta r. The displacement, or change in position, is the final minus the initial. As always, when we have the change in something, what we mean is the final thing minus the initial thing. If I wanted to see the change in my bank account over the course of a month, I would take the final value minus the initial value. It's the same thing here. The change in the position vector is the final minus the initial. So we can write the definition of displacement here as RF minus RI. We can also write this in terms of components. I'll do the x component in orange again. And going from here to here, the bug went this far sideways, call that delta x, and the bug went this far down. We'll call that delta y. So we can express the displacement vector as components. This far sideways plus this far up and down. That's its definition. An important thing about the displacement vector, an important thing to notice is that the displacement vector delta r here depends on the initial position and the final position. It depends on the endpoints, but it doesn't depend on the path. I drew this curving path in light blue for the bug to walk on, and it gave us that displacement vector. But there are an infinite number of other paths that would give us the same displacement vector. There's nothing in this definition here that tells us what path the bug actually took. The bug could have taken the straight line path between those 2 points, and have the same displacement vector. The bug could have gone this way with the same displacement vector. The bug could have taken this path, and they would all have the same displacement vector. So long as you begin and end at the same places, you have the same displacement vector. The displacement vector tells you nothing about the path. It's path independent. That's an important thing to remember about the displacement vector. It tells you nothing about the path. Okay, now let's move down to average velocity. I'm going to give you the definition first, and then we'll talk about what it means. Average velocity folds time into this business. So far we've looked at the position vector and the change in the position vector, but we haven't said anything about how long it took. The bug took this curving path between this point and this point, but we haven't factored in how long the bug took. If the bug took a very short time to travel this distance, then it would have been moving quickly. If it took a very long time, the bug would have been moving slowly. And clearly, those are two different motions. So we bring time into this when we define velocity. Average velocity is defined this way. V for velocity, average, and this tells me it's again a vector. The average velocity is the displacement divided by the time. I can write it in terms of components. Because the displacement has components delta x and delta y, I can write it this way. This is the x component of average velocity. It's how far you moved sideways divided by how long it took you. And this is the y component, how far you moved up and down divided by how long it took you. So that's what we mean by average velocity. To get at the notion of instantaneous velocity, let me erase this stuff on the figure because it's too crowded now to make much sense of. And I'm going to draw it again, and we'll talk about instantaneous velocity. Okay, so there's the bug at 2 times. Now, we've realized that the displacement and the average velocity are the same no matter what path the bug took. So we know it was here, and we know it was here, and we know how long it took. That's it. I don't know if it took this path or any other path. If I want to pin down the motion of this bug more precisely, then I need to look not only at this time and at this time, but I need to look a little more often. So suppose I looked halfway in between those 2 times, and I found the bug right there. Well, I could define a displacement between those 2 points, delta r. If I knew how long it took, I could find an average velocity. Notice the average velocity is always parallel to the displacement. On average, the bug was going this way. But still, that doesn't tell me what exact path the bug took. I just got one more point on the bug's path. If I want to narrow this down even more, what I want to do is add yet another location for the bug when less time has gone by. And now the bug is here. And I can draw this displacement vector. And I can calculate this average velocity. And notice that the average velocity is starting to track closer and closer to the shape of the path that the bug is actually taking. If I do it again, and I look an even shorter amount of time, so that now the bug is just right here, the displacement is now this way, and it's coming close to parallel to the path. So as I shrink delta t, the time between instances when I mark the bug's location, as I shrink that delta t smaller and smaller, I come closer to mapping what the bug is doing at this instant here at the beginning. That brings us to the notion of instantaneous velocity. It's defined this way. Instantaneous velocity is just v, and it is the limit as delta t goes to 0 of the displacement over the time. Now, You know from your calculus that what I'm defining for you here is the time derivative. So this is dr dt. Instantaneous velocity is the time derivative of the position vector. It tells you how the position vector is changing at a particular point in time. So imagine shrinking this down to, or shrinking the time between observations down to 0. The bug moves almost no distance in almost no time. And that ratio is the time derivative. It tells you how fast and in what direction the bug is moving at a particular time. And because it's the derivative, this velocity vector, I'm going to draw it in red, this velocity vector is always going to be perfectly parallel to the path. We'll draw some velocity vectors here. It's going to be tangent to the path. The velocity vector tells you two things. It tells you how fast something is moving at a particular instant, and it tells you what direction it's moving in. Now, before we define anything else, let me give you some units here. If we back way up to the beginning, the position vector is measured in units of meters. You're so many meters left or right or up or down. Displacement vector is also in meters. These velocities include meters in the numerator and the unit of time in the denominator. So velocities are always measured in SI units, in meters per second. Okay, so there's the units in parentheses at the end. Okay, now let's define average speed. To get at that, let me again erase some of this so we clear the figure up. And I want to go back to something that I mentioned about displacement and average velocity. And it's the fact that the displacement depends on the endpoints, but not the path. Here are two paths that the bug might have taken between these endpoints. There's one, and I'm going to draw another one that is much longer. So the bug takes some long meandering path. Now let's suppose it took the bug the same amount of time to travel each of those paths. To travel this path that we had first, it took the bug, let's say, 10 seconds. And then to travel this much longer path, it also took 10 seconds. They both have the same average velocity because they have the same displacement in the same time. But there's something clearly very different. The bug was traveling faster on that longer path. And we get at that through the notion of average speed. Here's the definition of average speed. I'm going to write it this way. S for speed, and then average. Speed takes into account not the change in position, not the displacement, but the total distance that you travel. The total distance divided by the total time, delta t. In other words, if the bug walked this big winding path here, imagine this was a string. We stretched it out and measured it. That's what goes in the numerator for average speed. It's the total distance that the bug traveled. If it took this shorter path, we would have a shorter string, and we would get a shorter average speed. This is a scalar. There's no direction associated with average speed. It just tells you, on average, how fast you were moving. Its units are also meters per second. Okay, I'll do an example in a few minutes illustrating, again, the difference between average speed and average velocity. It's an important difference. Okay, instantaneous speed. That is a scalar, and it is the magnitude of the instantaneous velocity. So it is the magnitude of the time derivative of the position vector. The instantaneous speed is what the speedometer in your car reads. If you're driving down the road and your speedometer says 60 miles an hour, 60 miles an hour is your instantaneous speed. It's how fast you're moving at a certain time. Okay, so that's the instantaneous speed. Also measured in meters per second. This guy is what your speedometer reads when you're driving down the road. Let's define acceleration, and then I'll go back and I'll say a little bit more about a couple of these terms. You can probably see the pattern of what's happening here. I told you before that mechanics is about the position vector and how that vector changes. And you can see that here. Here's the position vector. Here it changed. Here it changed over time. Here's its time derivative. The same pattern is going to follow now. Acceleration is the change in the velocity in the same way that velocity was the change in position. The velocity of an object is how the position vector changes over time, either average or instantaneously, and we want to carry that definition through here. So when we define acceleration, average, we mean change in velocity over change in time. Velocity is a vector, so there are components here. So we can write delta Vx over delta t. There's the x component of the average velocity. Or we could write delta Vy over delta t j hat, the y component of the acceleration vector. Now that's an average quantity. Over some finite amount of time, the velocity vector changed. We can imagine this limiting process again. If we look at how the velocity vector changed over shorter and shorter periods of time, I'll come back and draw some pictures and talk about this in a minute, we get at the notion of instantaneous acceleration. How is the velocity vector changing at a particular point in time? So A is the time derivative of the velocity. It's the rate of change of the velocity vector. Velocity tells you how the position vector is changing. Acceleration tells you how the velocity vector is changing. Now, because velocity is the derivative of position, you can write this as the second derivative of the position vector. And of course, you can write it in terms of its components also. I'll write those here. This is dvx dt I hat plus dvy dt j hat, and one more. The x component of acceleration is the second derivative of the position along the x-axis, and the y component is the second derivative, I'm missing my 2's here, second derivative of the y component along the y-axis. Okay, so there's all of our definitions. Units. Acceleration is in units of meters per second squared. Same thing down here. Now let me erase this plot and draw some pictures and talk a little more about velocity and acceleration. All right, let me draw for you a velocity vector. So here's a velocity vector. That tells me two things. It tells me the object, which has this velocity, is traveling in this direction. And it's traveling at a speed given by the magnitude, by the length of this thing. The longer that velocity vector is, the faster the object's traveling. Whatever direction that velocity vector is pointed in is the direction that the thing is traveling in. Imagine if you were in your car, driving down the road, that there's a vector pointing out from the hood of your car. The longer that vector is, the faster you're going. It's tied to your speedometer. As you speed up, that vector gets longer. As you slow down, that vector gets shorter. And it's always going straight out from the hood of your car. So that if you turn left, that vector swings to the left. If you turn right, it swings to the right. The velocity vector is telling you those two bits of information. It's telling you how fast you're going, and it's telling you what direction you're heading in. If someone wants to know either of those, you get those bits of information from the velocity vector, how fast you're going and what direction you're heading in. Now, what does acceleration tell us? Let me add on to this velocity vector an acceleration. So suppose we are accelerating in this direction. Acceleration tells you how a velocity vector is changing. So what I have here is a velocity vector that's changing in this direction. So that as time goes by, this blue vector is going to get longer and longer and longer because it's changing in the direction of the acceleration. This object is speeding up. Its velocity vector is getting longer. Here's the opposite case. If the acceleration vector was this way, then here's the velocity vector, but as time goes by, it's changing in this direction, and it's getting shorter and shorter and shorter and shorter and shorter. This object is slowing down. When the acceleration is in the same direction as the velocity, the object's speeding up. When the acceleration is in the opposite direction as the velocity, it's slowing down. Now what happens if the acceleration is perpendicular to the velocity? Suppose the acceleration is this way. In this case, the velocity vector is here, but it's changing in this direction. So this is like if you were in your car, you would be turning left. So imagine you turn left, and this velocity vector starts to rotate. The velocity vector is always going to change in the direction of acceleration. This object is turning to the left. Here's the case where the object is turning to the right. This velocity vector is going to change in the direction of acceleration, and it's going to rotate around this way. You can, of course, do both things at the same time, speed up or slow down, and turn. Let's draw this example. Here's an acceleration vector. This object is speeding up and turning left. It's speeding up. Let me draw that component in red due to this component of the acceleration. Later in the course we'll call that the tangential component. And it's turning left from this component of the acceleration. Later in the course we'll call that the centripetal component of acceleration. And this is a right angle in here. But this object is speeding up and turning left. Okay, so a good way to picture the velocity vector is to think of driving down the road in your car. The faster you go, the longer that velocity vector is, coming straight out of the hood of your car, and the direction of it tells you the direction that you're heading in. The acceleration vector tells you how that velocity changes. So those are our definitions. That's our kinematics dictionary. So let's have a look now at some animations so that we can see an object and its position, velocity, and acceleration vectors as it moves along a curved path. After that, we'll look at some examples and do some problems.